Howdy. I'd like to talk to you a little bit today about how differentials can be used in physical sciences to estimate quantities efficiently. And to get there, I'd like to consider two shapes that you're familiar with. One of them is a circle, and the other is a cube. Let's come over to the circle here and give it a radius of r. And when we give it a radius of r, we can also compute the area, which of course is pi r squared, as you are familiar with from geometry. Now we want to ask an important question. How does the area change as r changes? There are two answers to this question. There is an exact answer, and the exact answer we're going to call delta A. It is the amount that the area actually changes by when r changes by a little bit. Let's go back up to the circle here, and let's let our radius change by a small amount, delta r. And when we do that, we get a new circle that is larger than the old. If delta r was negative, we get a new circle smaller than the old. And the area that we add on when we expand our circle is all of the blue shaded stuff right here. And that's our delta A. And if I wanted to compute delta A, then what I would have to do is to evaluate the area for a circle of r plus delta r, and then I would have to evaluate the original area and subtract that off from the new area to get a change in the area. Well, that's not so bad. But Leibniz is going to come along and he's going to say, guys, we can estimate this much easier. And the estimated answer is going to be dA, the differential in the area, which, as you remember from class, is equal to the rate at which the area changes times the change in the radius dr. And since the area is equal to pi r squared, it's easy enough to compute the derivative, which is 2 pi r. And so I have an easy formula for the way in which my area changes as the radius changes. The change in the area will simply be 2 pi r times dr. Notice that in my formula, I'm going to treat delta r, the actual change in the radius, and dr, my differential change in the radius, as the same quantity. As long as my radius does not change by a whole lot, there's no harm in doing that. Now, how do these two answers compare to one another? Well, again, delta A is the exact answer. And the virtue that it has is that it is exact. But the liability that it has is that it is a little bit more complicated to compute. You can see that if I wanted to compute this, I would need to expand using algebra, and then I'd have to do the subtraction and so on and so forth. Whereas my dA, I have a formula ready to go. But there's an interesting connection between the two, and that is this. Let's take a look at what would happen if we did expand this. If I expand the square, I get r squared plus 2r delta r plus delta r squared. And if you distribute the pi, and then notice that you have like terms here and here that cancel, then what you're left with is an exact expression for delta A. That looks looks very much like dA, except that it has this additional term right here. And what Leibniz is going to say is that as delta R goes to 0, then delta R squared is going to go to 0 that much faster than the other term, 2 pi R times delta R. And you can see that if I take, for example, delta R is 0.001 inches or something like that, then when I square that, I'm going to get 10 to the minus 6, which is negligible in comparison with 2 pi R times delta R. And so what Leibniz is really doing with his differentials is that he is taking all of the terms that involve delta R or dr squared or higher orders, and he's considering them to be negligible. And what he ends up with is this guy right here. But what is also fascinating about this is that the expression that we have right here, the rate of change, just so happens to coincide with the circumference of the circle. And it turns out that's not an accident either. If you were to take the delta A that we have right here, and if you were to cut it loose from the circle by slitting right here and peeling off the entire circumference, then what you would end up with is a very long, skinny trapezoid whose area is equal to delta A. Now, the area of the trapezoid is the average length times the height. The height here is delta R, which is also dr. And the average length right here corresponds to the average circumference of the circle as you go around. So our delta A is equal to then the average circumference, or 2 pi times the average radius, times delta R. And that's, excuse me, I needed to label that correctly. That's our delta A. How does that compare to the dA? Well, the dA is equal to 2 pi R times dr. Remember that R was the original radius of the circle right here. So the dA is going to estimate the area of this trapezoid by taking the top side of the trapezoid to be the average radius. Is that true? No, it is not true. Is it close to true? Yes, especially when dr is really small. So how do we sum all this up? We can sum all this up by saying that there is an exact delta A that we could compute. But that delta A is a pain to compute because it involves some algebraic squaring. And we can say that there's an estimated change in area, and that estimated change in area is A prime times dr, which is 2 pi R times dr. And that estimated change in the area will be approximately equal to the actual change in the area for small changes in the radius. Notice that our variable that we control, which is the radius, the change in that radius we're going to label in two ways. We're going to label it as delta R because it's a change, and also we're going to label it as dr because it is the differential change in the radius. Let's come back now to our cube. We have a cube over here. We'll put them on a new page. And I want to do the same thing with the cube. Oh, come on. There we go. I want to do the same kind of thing with the cube that we did with the circle. Let's give our cube a side of S, and from that we can compute the volume. The volume, of course, is S cubed. And I want to ask the question, how does the volume change when the side changes? So there is, once again, an exact answer. And that is that the delta V is going to be equal to S plus a change in S cubed minus S cubed. And if we felt like multiplying it all out, we could expand that cube and subtract and cancel and so on and so forth. But superior to that is our estimated answer, which is going to be dV is equal to the derivative of the volume with respect to S, times ds. And since I know volume is equal to S cubed, then V prime is equal to 3S squared. And therefore I get my estimated answer, dV is equal to 3S squared ds. Very convenient, easy to compute. Notice that this has an interesting geometrical interpretation also. If you extend each side of this cube by an amount ds, like this, so, and like so, and pretend for a moment that my artwork is good enough so that each of these ds's is identical. So there's the ds and here's the ds. That's the same one we're looking at. Oh, we need to extend the top, don't we? There we go. So here comes my ds. And what I've really done is to add 3 new faces to my cube, and the volume of each face, dV, is going to be equal to S squared times the thickness ds. And since there are 3 faces, my dV will be 3 of those. Ta-da! And the key point that I want to get across is that for every differential, there should be a corresponding physical picture that makes sense. Now, I want to talk about 2 different ways that we can interpret the differentials. The first way that we can interpret differentials is exactly as we did in the previous slides. We can interpret dA equals A prime times dr as the answer to the question, how does A change when R changes? And that is a picture of dynamic motion. We're going to change R in some way, and A is going to change as a result. And there's a second way that we could think about it, and we could think about it like this. We could interpret dr as an error in the measurement of R. In other words, when I measured the radius of my circle, I had a ruler and I used that ruler, and my measurement technique and the ruler are only so good, and so maybe I measured the ruler and the radius with the ruler as 5.0 centimeters plus or minus 0.01 centimeters. And so we can think of the radius here as the measured value, and we can think of the error as a small differential change in that value. So instead of picturing the radius as being an exact number, we can picture it almost as like a fuzzy kind of value that is somewhere between 4.99 and 5.01. Just like that. Well, if I have an error in the radius, then I'm going to have a corresponding error in my calculated area. And so dA then would be an error in the calculation of A based on dr, the error in measurement of R. In other words, I calculated area equals pi r squared, but it turns out that my R is not a sharp, precise value, but instead is a slightly fuzzy value. It's r plus or minus dr. So how much does that affect my calculation of A? And we're going to call the error in the calculation based on another error a propagated error. In other words, I made an error in the measurement of dr. I couldn't help it. My instruments are limited and my technique is limited. I made an error in the measurement of dr, and that error now propagates to all the calculations I make with r. So, how much? Well, actually, it's easy to compute, because once again, dA is equal to A prime times dr. And so in our particular case, I can immediately compute that the propagated error in my calculation is going to be 2 pi times the radius that I have, 5 centimeters, times the uncertainty in my radius, which is 0.01 centimeters. And if you multiply all that, it gives you 0.1 pi. And that would be centimeters times centimeters, 4.3142 centimeters squared as the area, as the error, the propagated error in the calculation of my area. Related to this, I could also compute the relative error. And the relative error is going to compare the absolute error that I got to the amount, the measurement or the calculation of the area that I had to begin with. And the relative error we're going to define as dA divided by the quantity A, which in our case is equal to 0.3142 centimeters squared, divided by the original area that I would have computed based on the measured value of R, which was 5 centimeters. And that gives me which is the same as 0.1 over 25, which is going to be the same as 0.004, or sometimes we'll write it as a percentage, 0.4%. Just like that. The relative error gives us a better sense of how far off our calculations are. If I only know that my dA is 0.3142, I don't have any way to compare that. But when I compare it to the original area and I see that it's only off by 0.4%, then I can say, oh, that's a fairly small difference. We don't care too much about that. Notice that the relative error never has any units with it, because it is always going to be the error in the quantity measured divided by that quantity itself, and those have the same units and therefore cancel.